please post your queries there, and one after the other. At the end of the session, we will answer those queries.
Exactly.
All right. So without wasting further time, let us start with the presentation. I will just share my screen. All right. Just a quick confirmation. Can you see the screen?
Yes, yes, yes. Nice. No
Okay,
problem.
perfect.
And go for viewing.
Yep. All
Yes.
right. So
Thank you.
you have the presentation on your screen.
Yes, sir.
Perfect. So just to, for those of you who probably might be new to Antenpar, let me just give you brief introduction about Antenpar as a company. So Antenpar India is a 100% owned subsidiary of Antenpar GmbH, which is basically a company from Austria. And we have our headquarters based out of the city of Graz, which is a couple of hours drive from Vienna. And as you can see on the screen, this company is almost 100 years old. So it was founded way back in 1922. And in next 2 years, we will be celebrating our centenary year. So 100 years in existence. One of the key characteristic of this company is that this company is not listed on the stock exchange. Rather, this is owned by a charitable trust known as Santner Foundation. The main advantage of being owned by the charitable trust is that we do not have to take the profits out of the company and pay back to the investors. This allows us to reinvest a huge amount of money back into R&D, development of new technologies and new instruments, or other new models for the existing instruments that Antenpar deals with. And those of you who have been following Antenpar over the last 5-6 years would have noticed that Antenpar has introduced a huge number of newer technologies and new models onto the market to meet the current growing demand of the industry. All in all, we have 8 producing subsidiaries across the globe. So we have our manufacturing facilities in the Graz. We have our manufacturing facility in Germany, Switzerland, and also in United States of America. Globally, we are represented by 31 sales subsidiaries. Antenpar India was the 12th sales subsidiary of Antenpar GmbH. And the parts where we are not directly represented as a direct operation, we have distribution partners, and there are over 60 distribution partners which represent us in various countries. So that's how we cover the globe for providing our solutions. And Antenpar provides about 170 different measurement solutions for a wide variety of application requirements. Of course, today we are going to restrict ourselves to the microwave synthesis part. Talking about Antenpar India, we are headquartered in India in Gurgaon, which is the neighboring country city of Delhi. And we have our sales and service operations all over India. So we have total 9 offices, one in Mumbai, 2 in Gujarat, one in Hyderabad, Bangalore, Chennai, Kolkata, Guwahati, and recently we have started our new operations in Chandigarh. We also believe in total customer support in terms of not just uh, factory trained service engineers, but we also have 4 demo cum application labs. One is in Gurgaon, one is in Mumbai, one in Hyderabad, and one in Bangalore. And these application come demo labs are open for all our existing as well as prospective customers. And I would like to take this opportunity and use this platform to extend an open invitation to all of you. So in case if any of you would want to visit our application labs in any of these cities, please feel free. Please get in touch with any of my colleagues or directly with me, and we will arrange for your visit. And you can spend a day with your samples with our instruments at these demo labs. All right. So moving forward on the presentation. So today's topic is the solution that Antenpar provides for nanomaterial synthesis. So first, we will just go over the basics of the microwave synthesis and closed vessel synthesis and how it is different or what are the advantages of the modern technologies over the conventional techniques that we all have been using. Well, this is my email ID for those of you who may want to write to me for any queries or any specific application requirement. Please note down this email ID and you can send me an email anytime, and I'll be glad to respond with the required solution. So let's start with the first part of the presentation, the basic principles of microwave chemistry. So one of the first thing is, why do we use microwave chemistry or any kind of reactor, is to accelerate our chemical reactions. And how do we accelerate the chemical reactions? Of course, this is for the reactions that are temperature dependent, and the answer is heat. So by heating these reactions, we can accelerate the rate of reactions. So Arrhenius law, it states that any reaction which requires heating, if we can increase the temperature of the reaction by 10 degrees, then we can enhance the speed of the reaction by 2 times. Simply put, if we take an example of a reaction where we are using ethanol as the solvent. Now we all know ethanol at ambient pressure has a boiling point of around 80 degrees centigrade. So let us assume that the reaction takes about 8 hours to finish at 80 degrees centigrade. If we can increase the reaction to or the temperature of the reaction to 90 degrees, the same reaction which otherwise was taking 8 hours now can be finished within 4 hours. If we went to 100 degrees centigrade, it gets over within 2 hours, so on and so forth. If we can go on increasing the temperature, and we took the 80 degrees centigrade to 160 degrees centigrade as the reaction temperature, the same reaction which takes about 8 hours to finish now can be finished within 2 minutes. So increasing in the temperature reduces the time of the reaction. But how do we do that? We all know that no matter what is the temperature that we set of our heating mantle, uh, the ethanol will always start to boil at 80 degrees centigrade in this particular example. So how do we achieve the higher temperature? Is by creating pressurized situation. So if we were working with a closed vessel setup, and if we could create a pressure of around 4.5 bar, then we can take the boiling point of ethanol to about 120 degrees centigrade. Likewise, in order to reach 160 degrees centigrade, the vapor pressure of ethanol has to be 12 bar. So how we work is, we take the closed vessel, we start to boil ethanol at 80 degrees centigrade, the vapors are formed. Now, because the vessels are closed, the vapors cannot escape. So it will create some vapor pressure, and this will go on increasing the pressure inside the vessel, and that will also take the boiling point of the ethanol higher and higher. So if we had a vessel which can work up to 12 bar, or which can withstand a pressure of about 12 bar, then this low boiling solvent can be easily heated up to 160 degrees centigrade. So rise in temperature and of course the vapor pressure of the reaction vessel will result in lower temperature or reduced time. This is a typical setup of our conventional heating devices. So we have a hot plate, we have oil bath or water bath, and we use this temperature measuring device, or basically a thermometer, to measure the temperature of the oil bath or water bath, and then we have kept our reaction vessel inside. To save on the solvent, we are using the reflux condenser, so that all the solvent vapors are condensed and they are replenished back into the reaction mixture. Now, no matter what temperature we set of this hot plate, the boiling point or the temperature inside the reaction mixture will always be limited to the boiling point of reagents that we are using. This is because we are working with open system, or rather at ambient pressure. And here the maximum temperature that we can attain in the reaction is limited with the boiling point of the solvents that we are using. So if we are using ethanol as the solvent, then no matter what is the temperature of the hot plate, we will always be working at around 80 degrees centigrade. With closed vessel, we can go to much higher temperature because of the higher vapor pressure. We can take the boiling point to much higher temperature. And what temperature we can go with a closed vessel system will totally depend on what is the maximum operating pressure, or the maximum pressure that that vessel can withstand. So depending on the maximum operating pressure that the vessel can withstand, we can go to that high temperature. So the maximum temperature will be limited by the specification of the reactor. If we look at conventional heating, so typically we have the hot plate, we have the reaction mixture in a glass container, and the heat is transferred conventionally or convectionally, and it is slowly transferred to the reaction. So first our reaction vessel gets heated up, and that in turn will heat up the reaction mixture. And if we took an IR image with the help of a IR camera, this is what we see. We see that our vessel is at a higher temperature as compared with the reaction mixture. What happens with microwave heating? In microwave heating, typically we use vessels that are transparent to microwaves. So microwaves will not heat the vessel surface itself, but microwaves will pass through, and the microwaves will directly interact with our reagents, and we are able to generate the in situ heating. And if we take a IR camera image of a microwave heated process, then this is what we see. We see that the temperature on the vessel body is relatively at a lower temperature as compared with the reaction mixture. And that is what our objective is, that we want to heat our reaction mixture to a higher temperature. So in case of microwave heated setup, the temperatures are usually inverted. So we have an inverted gradient, and we have the reaction mixture at higher temperature rather than the glass walls. So how does microwave heating work? So basically there are two processes responsible, or two types of heating mechanism. One is dipolar rotation and other is ionic conduction. So what happens in dipolar rotation? Well, we all know that microwaves are part of the electromagnetic radiation, which basically are nothing but sinusoidal waves. So when the reagents are exposed to microwaves, then these molecules, they try to align themselves with microwave radiation. And in doing so, there is a rotation, and because of the rotation, there is a friction amongst the molecules, which creates instantaneous heat. So we get the reagents heated up under microwaves. The effectiveness, or how fast our reagents will get heated up, depends on the dipole moment, which means higher the polarity, faster will be the rotation, and more will be friction, and faster it will get heated up. Simply put, a solvent or a reagent which is high in polarity will be easier to heat up rather than a non-polar solvent which will be relatively difficult to heat up. So if we have something like ethylene glycol, which is highly polar solvent, and I want to go to higher temperature, it will be heated up very fast as compared to toluene, which is a non-polar solvent, which will take longer time. So this is one way of heating in presence of microwaves. Other way of heating is by ionic conduction. So here the molecules are present in ionic state. Again, these molecules, they will try to align themselves with microwaves, and in doing so, there will be rotation or rapid movement, and this will result in friction, which will create instant heat. In case of ionic conduction, the effectiveness is a function of concentration. So higher the amount or higher the number of these ionic molecules present in the solution, faster will be heating. An example would be if we take water, we want to heat it to, let's say, 100 degrees centigrade temperature. And let us assume that it takes about 2 minutes to reach 100 degrees centigrade with microwave heating. And I add a pinch of salt. So now I have NaCl in ionic state available in the microwave, this water. And then I want to heat that water with some amount of salt in it. Then to reach 100 degrees centigrade, it, instead of taking 2 minutes, it will probably take, let's say, 1.5 minutes. I add another salt, pinch of salt, and it will heat it up even faster and faster. So as I go on increasing the concentration of salt inside the water, the heating will be faster and faster. However, in both the cases, the heating is direct in core. So which means we are using the vessels which are transparent to microwave, and directly the microwaves will interact with the solutions or the solvents or reagents, and the heat is generated from within the sample. And the interaction of microwaves is determined by what we call as loss tangent or tan delta. Simply put, it is basically a measure for converting the electromagnetic energy into heat. So if somebody said this particular solvent has a higher loss tangent, it means it can be heated up fast in presence of microwave. If I said that this particular solvent has a lower loss tangent, it means it will be slower in to get heated up in presence of the microwaves. There's an example that as we go on increasing the concentration of NaCl, the heating becomes faster and faster in presence of microwave. Rest everything remains same. So do microwaves have any magic? Do they affect the reactions in any way other than heating? Well, this thought comes from the fact that we all know that many of the organic reactions can be affected in presence of UV radiation. So UV radiation can actually cleave bonds, and it may change the way a reaction progresses. Uh, Microwaves are also a part of the same electromagnetic radiation. So by that virtue, would microwave also affect my reaction in any other way, or whether it can cleave the bonds? The answer is no. All that microwaves do is they only heat. They generate instantaneous heat, and that's it. Because microwaves, if you look at the entire electromagnetic radiation, then as we see that on the left side, we have high energy radiation, which has gamma rays, X-rays, or UV rays. And as we move towards right hand side, we have these microwaves and radio waves, which have very, very low energy, which cannot cleave the bonds. Well, for everybody's information, all the uh, instruments which use this radiation, they are permitted to use frequencies of 2.45 gigahertz. So all microwaves, whether we are using in our kitchen or whether we are using for scientific research, they all have a frequency of 2.45 gigahertz. So there is an example, the quantum energy of different radiation. As you can see with microwaves at 2.45 gigahertz, the quantum energy is just 0.0016 electron volts. The simplest of the bonds also have energy requirement of 0.21 electron volts. So as you can clearly see, the microwaves cannot break the simplest of the bonds. So it has very, very low energy. So microwaves only induce vibrations among the molecules, and due to which there is an instantaneous heat generated. That's it. Based on the microwave absorptivity, the various solvents are classified into high absorbing, medium absorbing, and low absorbing. So as you can see closely, this is nothing but we are moving from highly polar solvents to non-polar solvents. So higher the polarity, it has higher tan delta or excuse me, higher loss tangent, which means it can be heated up with microwaves much easier as compared with the low absorbing solvents or non-polar solvents, which have lower loss tangent, and they will take longer time to get heated up with microwaves. So, all right. So why do we even need microwave heating? Because it's fast and uniform when compared with a conventional heating setup. So in case of microwave heating, the solvents and reagent absorb microwave energy because we use vessels which are transparent to microwaves, and we are able to achieve direct in-core heating. Also very, very important is that in case of any reaction which can become spontaneous, the microwave energy or the source can be instantly switched off. So there is no external energy being provided to the reaction, and we can handle the reaction more accurately or in a much safer way. And of course, comparatively, it is more energy efficient because you don't run the reactions for a very long period, and the heat is also not transferred very slowly. Well, we have seen this. So if you look at the advantages of using closed vessel reactors, because with closed vessels we are able to go to high pressure and high temperature. So we are able to achieve enhanced temperature and rapid superheating of the solvents in sealed vessels. So we can easily achieve the high pressure conditions, which result in faster reaction because of the Arrhenius law. And more often than not, we are able to achieve higher yields. Now, remember, I said that microwaves do not have any impact in the way a reaction will progress because it cannot, cleave the bonds. Still, I am making a claim here that typically we have higher yields. This higher yield is because of the lower formation of byproducts, because when we are using conventional heating setup, in order to reach your, let's say, 100 degrees centigrade, it will take 20-30 minutes to reach that temperature. And also the cooling is very, very slow. So along this heating and cooling curves, there is a lot of byproducts are formed. As against this, in case of microwaves, the heating is very, very fast. So you have very sharp curves, so which does not allow to form byproducts so much. So when we have less byproducts, our purity of the compound or target compound is much higher. So we are able to get higher yields. Also, with the closed vessel, we are able to finish our reactions very, very fast. So this allows us rapid reaction screening and optimization of the condition. So if I had a open vessel setup and a reaction that takes about 8 hours, so in a day I can only perform one reaction. With microwave, the same reaction can be performed within 2 minutes or 5 minutes. So I can perform much many more reactions in a day. So I can screen my reaction much faster. Also, there is a complete control over the reaction parameters, so I get always reproducible and accurate results. In addition to this closed vessel, what are the additional benefits of microwave heating is that we are able to achieve direct in-core heating, so we have rapid energy transfer. There are no temperature gradient, so we can totally eliminate the possible wall effects. We can also use catalysts for selective heating and see if there are any specific effects. And we can also automate the microwave reactor by using a robotic autosampler, or by going for parallel synthesis, where we can in parallel process multiple number of vessels at a time. So we can increase our sample throughput. So when we talk about microwave, there are two types of instruments. One is monomode instrument, which is ideally suited for the small scale reactions, where I may want to synthesize say milligrams to maybe a couple of gram of material. And there is another type that is known as multimode reactor, where I can parallelly run multiple vessels and I can synthesize say anywhere between 50 grams to maybe 100 grams depending on the reaction in a single run. So the major difference between the two is that in case of a monomode cavity, we have a small cavity size, typically around 100 to 150 ml, where we keep a single reaction vessel of around 10 to 20 ml volume, because we are interested in synthesizing few milligrams to maybe a couple of grams of sample. And there is a single magnetron which produces microwaves. There is a waveguide which basically will focus this microwave onto the sample for effective heating. So the micro energy is created by a single magnetron and directed through a waveguide onto the sample, and we create a standing wave kind of a situation, and the heating of the vessel takes place. As against this, in case of a multimode reactor, we use typically large cavity sizes of around 50 to 60 liters. And because of the large volume of the cavity sizes, a single magnetron may not be sufficient because it will not produce enough energy, and the field intensity of microwave may not be very high. So typically in case of multimode cavity, we use higher installed power. So typically two magnetrons are used which produce microwaves. These microwaves are introduced onto the cavity and then they are just thrown inside. The microwaves will get reflected back from the walls of the cavity to the center of the reaction, where we have kept bigger vessels of around 100 ml which are filled around 50 to 60 ml, and like that we can have multiple 8 or 12 or 16 vessels at a time, and they get heated up in presence of the microwave. So we have multiple heating points because of the large volume of the vessels. So that is how it works. So that is the difference mainly between monomode cavity and a multimode cavity. In monomode cavity, we can process one sample at a time. In case of multimode cavity, we typically have multiple reactions running in parallel. So the major difference between the two, the monomode cavity and multimode cavity, is smaller cavity size with monomode instruments as against the large cavity size of the multimode cavity. Monomode instrument, as I mentioned in the beginning, are ideally suited for small scale run, where we can process between 0.5 ml to 20 to 30 ml of the volume. In case of multimode cavity, it is ideally suited for the large scale runs up to 1 liter. With monomode, I can have limited scale up possibilities. Say I want to synthesize about 10 grams of material, then I will take same reaction in multiple vessels, and one after the other I will run that, and I can probably every run I can synthesize something like a couple of grams. So I can synthesize 10 grams of material by having same reaction run 5 times. But if I wanted to synthesize 100 grams, then definitely running 50 reactions one after the other will be quite tedious. So it has limited scale up possibilities. In case of multimode cavity, I use large volume vessels of around 100 ml, which can be filled up to 60 ml, and we could process up to 16 samples together, so 16 reactions together. So we can ideally go for scale up reactions without a problem. A monomode, we can increase the throughput by having an auto sampler, a robotic arm, and with multimode, we can have high throughput by parallel synthesis. But whatever reaction you can perform with monomode can be performed with multimode and vice versa. So as far as the chemistries are concerned, they both work fine with either of the technique. So the choice mainly depends on the individual application, whether we want to do screening and optimization of the methods, or we want to produce large quantities of the material. If our objective is to screen and optimize the reaction condition, obviously a monomode is much simpler as compared with a multimode instrument. And also the required reaction conditions of pressure and temperature and the reaction scale. So if we wanted to go to near critical water chemistry kind of applications and very high amount of reaction scales, then a multimode cavity will be more suited. So that is a major practical difference between the two. So when we talk about the what I have tried to do is I have tried to keep this topic only to the nanomaterial synthesis, because that is what today's agenda was. So what are the major challenges that people usually face when we are working with nanomaterial synthesis? So if we talk about the nanomaterials, in nanomaterials, we are transforming solids into liquids. Special structures will provide unique properties to the nanomaterial. For example, I may have carbon as the base material, but a carbon nanomaterial in spheres or a nanotube uh, may have totally different physical properties. And the size and shape and dimensionality uh, of these nanomaterial, they highly affect the properties of the final material. And while synthesizing, just by changing slightly the environmental parameters, for example, a temperature or the pressure, or whether we have inert atmosphere or some reactive atmosphere, we can totally alter the crystal growth during the synthesis. So how does microwave help to synthesize the nanocomposites? The microwave irradiation quickly and conveniently provides access to high temperature. It helps to quickly tune and optimize relevant synthesis parameters. In combination with accurate temperature measurement, it ensures that we have highest convenience and highest reproducibility. So whatever reaction we have performed today, maybe 6 months down the line, I want to perform the same reaction. I just take that method and run my reaction, and I will be assured that I will get the reproducible results. So microwave in essence is a rapid, convenient, accurate and reproducible technique for synthesis of nanomaterials. But as is the case with everything else in the life, uh, we also have challenges when we do nanomaterial synthesis with microwaves. So what are the challenges? Uh, Most of the times, many of the nanomaterial synthesis, we require very high temperatures, up to 300 degrees centigrade. We want to reach fast to higher temperatures so that we can have uniform distribution of the morphology, so that we do not have to spend a lot of time later in filtering out the nanomaterial or the morphology of our interest from rest of the material. Many a times they require to be held at very high temperature for very long period, maybe 2 hours, 3 hours also, in order to form a particular morphology. Also, they need to have efficient stirring. Otherwise, we will not have uniform temperature distribution across the volume of the vessel. And if we don't have uniform temperature, then obviously we will not have a good, morphology spread across the volume. Also, we don't want any interferences from the previous reaction. So we need to have a reaction vessel which is having a very clean material, like for example, cords could be one of the materials where we can do the nanometal synthesis without any interferences from previous reactions. Also, as I mentioned in the previous slide, slight alteration in the reaction condition can affect the morphology that I am interested in. So we need to monitor and control the temperature very precisely, and many a times we require to use inner atmosphere. So we also need to maintain the conditions inside the reaction vessel properly. So these are the usual issues. Now, going to high temperature, most of the reactors, they use PTFE vessels when we are talking about microwave reactors, and PTFE vessels have a limitation of temperature. They can only work nicely about 230, 240 degrees centigrade. So if I wanted to use water as the solvent and go to 300 degrees centigrade, or may want to perform near critical water chemistry, then PTFE is not a good choice. Then I require another material, something like cords, which can withstand those kind of temperature without a problem. Also, we will see in the next slides that how, as we reach high temperature, the heating can become difficult. The same solvent which has a good heating profile at a lower temperature, as we go to high temperature, the solvent tends to become more transparent towards microwave. Also, because uh, there is a possibility that some of the microwave radiation may be reflected back and the magnetron may get overheated. So many of the microwaves do not work at very long holding times. So if I wanted to go to high temperature, typically, the reactors will stop working after half an hour, 45 minutes. And of course, PTFE is not the cleanest reaction vessel material that we all know. So these are some of the challenges that microwave reactors or synthesis of nanomaterial with microwaves we face. So talking about how Antenpar can provide the solution to this. So we have these wide product portfolio. We have monomode instrument, which is monowave series, that is 200, 400, and 450 is monowave 400 with an auto sampler. So we can process up to 24 samples one after the other. So we can perform reactions 24 numbers unattended. So after one reaction is over, the robotic arm will pick the vessel out and place it back onto the auto sampler and move on to the next reaction. So these are but for the small scale reactions. So typically between 0.5 ml to 20 ml, we can perform the reactions. If I wanted to go for scale up, we have Multiwave 5000, which is a parallel reactor, which can process up to 16 reactions at a time. Or I can use Masterwave BTR, which is a single 1 liter reaction vessel, and I can synthesize between the two anywhere between 50 grams to maybe 200 grams of material. And these are the typical applicable reaction scales. So these are the vials which are used with monomode instruments. So we have 0.5 ml as the lower side of the volume, and with higher vessel we can go up to 20 ml. These are the parallel vessels, rotors as we call with microwaves. So as you can see, there are multiple vessels. So these vessels are 100 ml volume, which can be filled up to 60 ml. And like that, we can process 8 or 16 vessels, as you can see in this rotor. So we can synthesize or process 16 by 60 ml of the volume. That's about 960 ml. So almost a liter. And this is a one single vessel of 1 liter, which can be filled up to 750 ml. And because of the sheer large volume, the normal stir bars will not work. So with this vessel, we have a mechanical stirring device. So this mechanical stirrer goes inside to ensure that we have a uniform stirring and we have a uniform temperature distribution across the volume. So typically, as I said, every solvent will have, if I want to heat it to a certain temperature, it will have a certain vapor pressure. So monomode instruments are typically rated maximum up to 20 to 30 bar. So a reactor which has 30 bar as the limit of operation for pressure. So we can heat the most commonly used solvents anywhere between 170, 180 degrees up to 200, 220 degrees centigrade. If we wanted to go beyond that, for example, if I wanted to use water as the solvent and go to near critical water chemistry, which is close to 300 degrees centigrade, then obviously this 30 bar pressure is not sufficient, because with water I want to go to 300 degrees centigrade, the vapor pressure is around 80 bar. So I need to have a rotor and a vessel that can withstand 80 bar of pressure. So that is where the multi-mode reactors come into play. So multi-mode reactors with specific vessels can work up to 80 degrees centigrade and 80 bar of pressure and 300 degrees centigrade of temperature. Also, there are various options available, like if I wanted to have a particular gas, inert atmosphere or inner reactive atmosphere inside the vessel. So there are gas loading accessories available. So before I start my reaction, we can introduce various gases or inert atmospheres inside the vessels, and we can also do pre-pressurization up to 20 bar. Then with monomode instrument, we also have a possibility, because there we use these borosilicate glass vessels. So we also have a possibility of capturing the images and creating videos of the reaction. So with monomode instrument, we have this camera feature available, so that while the reaction is progressing, we can see how the reaction is taking place. We can capture the images and also create movies. There's an auto sampler or robotic arm for unattended processing of up to 24 reactions. Then of course we with the multimode rotor, we also have a possibility of silicon carbide plates, where we can use the small volume vials and we can process up to 192 reactions in one go parallelly. Somebody who's working with ionic liquids, so ionic liquids, as the concentration increases, the absorbance of microwave rapidly goes high, and the temperature can shoot up very, very fast. So IR temperature sensor may not be sufficient. So we also offer internal temperature probe with our monomode instrument. So this Ruby thermometer can work as an additional temperature probe in collaboration with the IR sensor, and we can see both temperature profile on the screen. So these are some of the available options with our microwave reactors. All right. So when we talk about the microwave in general, these are some of the challenges that people face. We can only use polar solvents, and non-polar solvents are not supposed to be used. These were the challenges faced by the scientists. Heating of the low boiling solvents to elevated temperature can be another challenge, because remember I said it depends on the pressure limit of the vessel that we are using. Scalability can sometimes be a challenge. Aggressive chemistries, many of us want to do use alkaline solutions, or we may also want to do fluoride chemistry. So glass vessels are not compatible, so there we may need to use different type of material. So these are some of the challenges. And Anton Par has overcome these challenges. So with N10 power instruments, we can heat polar as well as non-polar solvents without any problem. Like we could heat the toluene to 200 degrees centigrade within 5 minutes. There's an example of toluene that with glass vessels, we can heat it to 200 degrees centigrade in around 5 minutes without any problem. Then heating of the low boiling solvent, the reason is, available. Many of the microwave reactors have a lower operating pressure range, only around 20 bar. So we can only heat low boiling solvents around 150, 160 degrees centigrade. So with N10 bar, we have made it 30 bar as the operating limit. So ethanol can easily heat it to 200 degrees centigrade. We all know what difference 40 degrees centigrade can make. It can really multiply the rate of reaction by 16 folds. So it can really reduce the rate of, the total time of the reaction to a very, very great extent. Just a difference of 40 degrees centigrade. So because of the high pressure limit, we can go to higher temperature with low boiling solvents. Scalability is no problem. We can take, if I'm working with some unknown reaction and I just want to optimize the reaction conditions before I can go to scale up. So I can take as low as 0.5 ml, standardize my reaction conditions, and without wasting a lot of time and money on re-optimizing of the condition, I simply increase the volume and I can scale it up to 20 ml within the monomode reactor. Or if I am having also a multimode reactor, then I can simply scale it up to almost 1 liter without any problem. The reason is all the vessels are rated to the same temperature and pressure limits. So we can get seamless scale up. So we can use the smallest vial, take only 0.5 ml volume and scale it up within the system up to 20 ml. So that is 40 times scale up. Or we could go almost 960 ml from 0.5 ml or 750 ml from 0.5 ml. So huge scale up possibilities are available. Aggressive chemistries can be an issue. Like, if I wanted to do in situ fluorination or alkaline solution heated at high temperature, with glass, they can really damage the vessel. That's why they are not allowed. So what we do is we offer a unique silicon carbide vessel, and silicon carbide, as we all know, is totally chemically inert material, and it allows these kind of reaction where glass material will be destroyed. So this typically is what happens to glass vessels when we are using fluorination or alkaline solution. And with silicon carbide, we can get rid of these problems totally. And also another advantage with silicon carbide vessel is that it offers us unlimited reusability. So actually, if I'm using a monomode instrument and I'm using a silicon carbide vessel, probably the silicon carbide vessel will outlast the instrument itself. So this is the model monowave 200, which is upgradable to monowave 400. It has maximum temperature of 260 degrees and 20 bar of pressure. It has all three type of vessels of 4 ml, 10 ml, and 30 ml. It can use silicon carbide vessel without a problem. And it can be upgraded to monowave 400, which comes with integrated camera option. And it has a maximum temperature of 300 degrees and pressure of 30 bar. When we take 400 and upgrade it with a robotic arm auto sampler, it becomes monowave 450. So monowave 450 will have 24 position auto sampler and all the features of monowave 400. So these are the typical, any small scale reactor that you take of microwave. So you will have these type of vials, and these vials are sealed with the help of these snap caps and uh, the septums. So among these different type of vials, we have the possibility of working with reaction volumes from 0.5 ml up to 20 ml. And of course, these glass vials are also reproducible. And similarly, we have these silicon carbide vials available in 10 ml and 30 ml volume. With silicon carbide vial, it also offers us additional benefit of heating even the most microwave transparent solvents. So I told you that with anten bar we can heat 5 ml 12 into 200 degrees in something like 5 minutes. With silicon carbide we can go to 250 degrees in less than 100 seconds. So really fast heating even for the non-polar solvents. With camera, what I can do is I can, while the reaction is progressing, I can monitor my reaction. I can click pictures. I can create movies of my reaction. So it is helpful to check stirring efficiencies, if my stirring is taking place or not. If I'm working with polymer synthesis, as my viscosity increases, my stirring may become slower and slower uh, as the final material becomes thicker and thicker. So I can check if my stirring is taking place properly or not. I can check if my dissolution of the material is taking place. If there are any color changes, we can observe those. And also if we are using metal particles, then if there are any discharges taking place, those can be observed and clicked, and we can create movies for future reference. So that was about quickly about monomode instruments. Uh, then other part is multi-mode synthesizers. With anten bar, we have the model Multiwave 5000. So there is a Multiwave 5000 with different type of rotors available, and you can practically do all type of synthesis, which includes nanomaterial synthesis, hydrothermal reactions, organic synthesis. We can also go for pre-pressurized reactions. We can also use this for solvent extraction and derivatization. And if somebody wanted to do UV assisted reactions or microwave assisted UV reactions, then that is also possible, or microwave assisted photosynthesis as we call it. So these different type of synthesis reactions are possible with this instrument. Uh, as I said, especially for nanometal synthesis, those who want to work with microwave and do near critical water chemistry, there is a possibility with quartz vessels. We can go up to 300 degrees centigrade and 80 bar of working temperature. For the non-polar solvent, we also have special silicon carbide heating elements, which we will see in the coming slide, for efficient heating of solvents at higher temperature, and also for the non-polar solvents. And this instrument also has a possibility of pre-pressurized reaction with gas loading accessory. I will not go much into the details or specifications of the instrument, of course, but in today's time, uh, these instruments also have a very interesting feature, is that they can be remotely controlled uh, using a laptop, PC, or even a smartphone. So I might be sitting in Mumbai. My colleague is working on a reaction in, let's say, Hyderabad. I can have a remote access over my mobile phone, and I can set up the new methods, and I can control my reactions sitting away. So in today's COVID-19 situation, this can be really a very nice feature to have on the instrument. So I will not, of course, when we are using microwaves, the safety is very important, because we are dealing with high temperature, high pressure, microwave radiation. So the user needs to be totally, away from any of the hazards that this can pose. So all the safety precautions are taken. So I will not go much into that. So what kind of rotors are available? We have uh, high performance, high pressure rotor 8N, so which can work up to 300 degrees and 80 bar using these quartz vessels that you can see on the screen. And for higher sample throughput, we have rotor 16, so which can process up to 1 liter, almost 1 liter of the reaction volume. For nanomaterial synthesis, this is what I always like to offer, because this can work up to 300 degrees centigrade and 80 bar, so we can perform near critical water chemistry. And because we are going to such high temperature and high pressure, so safety becomes all the more important. So this has simultaneous control of all reaction vessel with individual pressure sensor. These white discs that we see are the individual pressure sensor sitting on top of every vessel. So simultaneously it monitors and measures the pressure inside every reaction vessel. And if any of the reaction vessel, the pressure goes higher than we have set, immediately it will regulate the microwave power and control the reactions. Of course, one of the things that we spoke about in the beginning is nanometal synthesis often requires extended run times at high temperature. As we know, PTFE and TFM vessels have maximum operating temperature of around 250 to 60 degrees centigrade. And when used under pressure, this also reduces drastically. So, we either can work with maximum pressure or maximum temperature specifications. So, as an alternative for extended run time at high temperature, quartz is an ideal alternative. It can withstand high pressure and temperature for extended period of time without any problem. So, when we are using quartz vessels, we can go to 300 degrees centigrade and even have hold times of 3 to 4 hours without a problem. There's again a repeat of the same slide that we saw, that it can work up to 80 degrees centigrade and 80 bar of pressure and 300 degrees centigrade of temperature. These are the special accessories, especially when we want to go to high temperature. What happens is, we need, because of the large volume of the cavity, we need more number of magnetrons which will deliver a higher amount of power. But as you can see for different solvents here, so we have ethanol, acetone, acetonitrile, water. As you can see, the dielectric constant, which is basically, simply put, is the microwave absorptivity of the solvent. So at lower temperature, they absorb very nicely the microwaves, but as the temperature rises, this dielectrical constant starts to drop. So higher the temperature we go, more difficult it becomes for the microwave to heat these solvents efficiently and maintain the heating profile. When we are using water, so at supercritical condition, that is around 374 degrees centigrade, water becomes totally transparent to microwaves. So at that temperature, I cannot heat microwave water at all, no matter how much power I am providing. So as we go to higher temperature, the microwave, these magnetrons need to deliver higher and higher amount of power so that they can maintain the heating profile well. So what we have to reduce the strain on the microwave, this magnetron, we offer the silicon carbide heating elements. So these silicon carbide heating elements, they will absorb microwaves 100%, and they also get heated up super fast, and they have a very fast thermal diffusivity, which means they also transfer the heat very, very fast. So silicon carbide this heating elements can be a nice tool when you want to work with these solvents at very, very high temperature. Again, these are totally inert, so they don't participate in your reaction. So they will no way, interfere in the reactions. No contamination of the samples at all. So this is the setup typically. This is an example where we take dioxane as the reagent, and with microwaves, it heats up very, very slow. So it's been almost, in this case, more than 5 minutes, and the temperature does not rise. There's like almost transparent to microwaves. The moment we add heating elements to it, you see within 1 minute, it crosses 100 degrees centigrade, and we can go to high temperature. So this is the advantage of using these kind of heating elements. Again, gas loading feature that we have. So there are accessories. Of course, these are available with many manufacturer. So there's an additional tool that you get with microwave reactor, that you can have pre-pressurized reaction conditions before you start with the microwave synthesis. So we can create either inert or reactive gas atmosphere inside the reaction vessel. So I'm not going too much into safety features. As we discussed, there are safety features already taken care of. Some application examples. So what kind of applications can be performed with microwaves? So we can do inorganic synthesis, which involves metal oxides, phosphates, silicates, zeolites, formation of quantum dots, preparation and validation of the catalyst. We can synthesize organometallic compounds, absolutely no problem. So all type of reactions that require temperature can be performed with microwaves without a problem. And of course, this is only related to inorganic, but we can also do organic synthesis. Absolutely no problem with microwaves. Only thing that we need to remember is that the maximum temperature of the reaction should not be at where our synthesized compound may decompose. So that is the only thing that we need to remember. So this is an example of nanocrystalline zinc sulfide powders. So when we are doing conventionally the synthesis of these nanomaterials, as you can see here, we have a spread of around 10 micrometer, uh, and the morphology is not very nice with microwaves because we are able to reach the temperature very fast, and we have efficient stirring inside, so we ensure that there is a uniform temperature distribution across the volume. So we are able to have nanometal synthesis or nanometals which have a good spread of the morphology, or they're not very widespread, but very narrow window of the sizes. Of course, N10 also provides small angle X-ray scattering instruments. So this is basically for characterization of these nanomaterials which have been synthesized. So we can, characterize them with the help of small angle X-ray scattering. Another example is quantum dots. So as you can see, within 15 minutes, we can finish the reactions. Or if I wanted to synthesize polymer coated nanorods, so we can go to a very high temperature very, very fast, which is required for these functional nanocomposites. We can have also a possibility of inert or reactive atmospheres if the need be. Another example is carbon nanotubes. This is our quartz vessel. Some molecular sieves. So we can go to, you know, 180 degrees centigrade or 200 degrees centigrade without any problem. Quantum dots. So we also have a lot of application reports available with N10 Power. So as and when you may require, we can provide. And we have also supplied, we have a lot of reference users of these instruments in the industry for various type of application requirements. So well, I this is all about a quick introduction of the uh, synthesis with closed vessels at N10 Power. So if there are any queries, we could take them.
Yeah, thank you, Dr. Dave. So almost the you touched from the different instrumentation and the different attachment or accessories which is available in N10 par also, and what is the different participate materials we can have for the synthesis. So
Yeah.
well covered. So shall we start for the question and answer session, if you
Yes,
don't mind?
please.
Yeah. Okay. The first question is, when we dissolve the solid type nanoparticles in water, the properties are same or going to be changed?
Uh, the properties of the nanomaterials or the
Properties of the nanomaterials.
well, when we talk about the water, usually we want to become, go towards a more greener approach on the synthesis. So people want to use water, and as we go high in the temperature, the water displays or it shows the properties of the other solvents. So usually, we will only be able to narrow down the distribution of these particles. So they will not change in terms of the properties, they will remain same, but our morphologies are more compact. We will be spending less time on purification process later on.
Okay, well,
Yeah.
so whether the solvent used are cost effective?
Yeah, water is certainly quite, that is the whole objective, that we want to use water. So it is definitely a cost effective solution, and also it is more environmental friendly. So after a reaction is over, even if we just dispose water into the environment, it is not dangerous for the environment, unlike the other solvents. So it has both cost effectiveness in terms of the money that we spend, and also cost effectiveness from the point of the money that we may spend on disposing these solvents safely.
Well, is the microsynthesis more advisable than any other physical synthesis?
As I said, microwave synthesis is advisable, yes and no. Yes is basically because it is rapid. It is very, very energy saving for us. We can really reduce the time that it takes for synthesizing this material. But if somebody wanted to synthesize, let's say, 100 kilograms of material, then obviously microwave will not be a choice of technique. But if somebody wanted, as long as I wanted to synthesize anywhere between milligrams to maybe a couple of kilograms in a day, then microwave reactors can be really a very good tool, because they can really speed up my reactions. They can reduce the wastage in terms of the byproducts which are formed. They will reduce the time that I spend in further purification because of the higher purity of the material that I'm getting. They will also help me to reduce the consumption of the solvents that I'm using for synthesizing. So if we look at these kind of aspects, then certainly microwaves definitely are helpful. As I mentioned in one of my slides, that microwaves are only heating tools with a lot of safety. So one should not look at microwaves as something which will alter the reaction altogether. So long as we are using it as a heating device, certainly it offers a lot of advantage over the other techniques. And also not to forget the reproducibility and accuracies of the parameter, because it's all software controlled.
Yes.
So these are the advantages. So yes, so any reaction which is temperature dependent, I would strongly advise that we can move on to the microwave, unless and until somebody is talking about synthesizing maybe a ton of material, then of course microwave will not be able to work.
So that was the next question. Can we
Yeah.
upscale the production to tons using this equipment?
The answer is no.
Yes,
But of
but
course, as is the case with most of the many application areas, where as we have reduced the sizes of the particles, the effectiveness, because of the larger surface area, is growing. Like, if you remember, when maybe 20 years ago, we used to take these medicines which had 500 mg, 1 gram of the active pharmaceutical ingredient. Now, because of the nano sizes, the amount of API required for the same kind of desired effect has reduced. So now we have medicines which are available in micrograms with active pharmaceutical ingredient. So if we have those kind of niche areas, then synthesizing a couple of kilograms a day would be sufficient. But I would say microwaves can be scaled up to kilolab applications and
yes,
not beyond that.
yes, yes. So how to increase iron concentration in water and ethanol?
Ah, well, this is something that would require more detailed explanation, and I think I will have to refer some document to answer this. Frankly speaking,
Yes, yes, yes.
yeah.
The next, very
Can I
one of
request you, sir, if you could just send me this question over email, so I will,
no,
send you
no, no,
the reply.
no, definitely, I will know all the chat box will be sent to you. But before,
Yeah,
let us clarify some of the doubts, and if it is, things are there, then we can have the
certainly,
session in the chat box. No
certainly.
issues. So if you
Yeah,
have another 5-10 minutes, okay,
yeah,
no
absolutely.
problem, no problem. Right. So okay. So is green synthesis possible through microwave?
Yes, that is the whole objective, as I said. When we talk about green synthesis, we are talking about saving of energy. We are talking about trying to move from solvents to water as the solvent. We are talking about reducing the consumption of the solvent. We are talking about making less and less usage of these environmental unfriendly reagents. So the whole objective, certainly with microwave we can move towards green synthesis, certainly, yes.
Yes. Uh, what is the scope of nanoparticles in future?
You name it, you name it. It starts from drug delivery,
Yes.
it starts from paints, it goes into food, it goes into packaging material, you name it. And every area uh, will have nanomaterial. One of the major challenges, as when we talk about agriculture, we face is this pesticide residue,
Yes.
which is very harmful for consumption of humans. So with nanomaterial, we can really reduce the dosage of these pesticides and insecticides, and with which offers the same kind of effect. So we can reduce the impact of these on the human health by reducing
Exactly.
the dosage with
Mhm.
having the same kind of effect. So I would
Exactly.
say nanomaterial has immense scope in practically every area that we can think of.
Okay. So there is a question: as the process time increases, dielectric properties reduces. Therefore, for how much time we can run the experiment in monomode setup?
Okay. Uh, as the process time increases, dielectric properties decreases is not correct. I'm sorry, but
Correct.
it is basically as the temperature rises, the dielectric properties go down. Uh, the reason that why one is, when I'm using microwave, my whole objective is to reduce the time as much as possible. However, uh, especially with nanomaterial synthesis, how long I keep these nanoparticles exposed to microwave also has an effect on the morphology of the nanomaterials. So with our instrument, we could be working at highest temperature, and we could keep them on for 3 hours, 4 hours without a problem. In fact, with monomode, we have a possibility of keeping the reaction on for 24 hours. With multimode, we can go up to 9 hours a reaction.
Okay.
But well, of course, that will be required, for research purpose. That what is the effect of such long exposure with the this nanomaterial properties or the morphologies. But ideally, I would like to reduce this as much as possible so that we can increase the throughput. But of course, in research, you want to explore all the possibilities.
Yes, it's all
So
depends upon the type of
exactly,
experiment what we are
exactly,
doing.
exactly.
Okay,
So maybe 8 to 9 hours is something which you can work absolutely no problem.
correct. So one of the tricky question is the farmers is benefited by using nanoparticles.
Yes.
Yes, why not?
Why not?
Yeah.
uh, because for example, if I am a farmer, uh, 10 years ago I had to buy uh, uh, pardon me, uh, 20 bags of urea, or 20 bags of material. So it cost me a lot. Today probably the same kind of impact I can see in my harvest by using smaller quantities of these chemicals, with the same kind of impact. And also that will have less impact on the quality of the soil that of my farm. So certainly, as a farmer, I will get benefited by this nano technology
Yes.
for sure.
So for the same question, there is a question as well as the answer from one of the scientists. Rules and regulations for marketing nanomaterials, though immense scope, but marketing question arises side effects of nanomaterials. And agriculture sector, so many products are there, but marketing same question arises of side effects. What is your opinion?
Yeah, rules and regulations for marketing nanomaterials through immense scope, but marketing question arises side effect of nanomaterials. Well, as far as the side effects is concerned of the nanomaterials, the side effects are as much as of that particular molecule.
Correct.
Uh, so in fact, with nanomaterials, we are going to use smaller quantities. Of course, their efficacy and increases because of the larger surface area. But again, if you really look at the absolute terms, then the amount of quantities that we will be using are much lower than otherwise, when we don't use nano technology in any area. So that will always remain, that what should be the prescribed limit. When we move to nano particle sizes, probably the authorities, they need to reduce or lower down the LOQs and limits of the quantitation, which can be really harmful. So it's a right, in my opinion, that is a right thought.
Yes. And again, anything excess is a dangerous. So
Absolutely.
not only the nano, not only the nano, anything is
Absolutely.
excess is a dangerous.
Absolutely.
And for that, we have fixed MRLs, minimum as well as the
Yes.
maximum.
Exactly.
All right.
Exactly.
So there is another question. What about the quantum dot, and what
Mhm.
is the purpose of those quantum dots?
Again, and for example, in case of the drug delivery system, so you want a desired impact of a pharmaceutical molecule or an active pharma ingredient, um, and these quantum dot coated nano pharma or nanomolecules, they can be effectively, by using smallest possible quantities, we can have them go to the sites where they are intended to. So this is to again reduce the side effects. For example, if I'm talking about medicine, then the objective is to reduce the side effects where the excessive medicine is given, and it may affect the other organs of the patient. So this is the objective, is to reduce the side effects of these pharmaceutical in medicine, for example.
Yes. So how nanocomposites will be cost effective for farmers?
Ah, anything, once it becomes, this is a tricky question, actually
Correct.
speaking.
Correct.
uh, any technology, when it is new, it is costly. But as this becomes available in mass, then obviously the cost of production goes down, and that will help the consumer. In case of the agriculture, the farmer is consumer when they are using these kind of things. So more and more it becomes popular in the usage, smaller will be the cost of operation for the manufacturers, and again for the consumer as a farmer, it will reduce the cost of these materials for the farmers. But as is the case with any new technology, when it is new, they are expensive, but over the period of time, they become cost effective.
Exactly. So as the new technology comes into the market, definitely there will be more cost, and day goes, automatically the cost is going to be reduced.
Exactly, because the consumption increases.
And also it's a demand and supply.
Exactly.
Most of,
Exactly.
most of the toxic effects of nanos arises from their synthetic protocols, that is synthesis protocols. Then how
Yeah.
much safe are the nano originated from microsynthesis?
This reminds me of one post I had read, those days of Yahoo Mail in 90s. So I had read one post, one forwarded email where they showed two plants. One was watered with normal tap water, other was watered with water heated in microwave and then cooled down and then watered. And this poor chap had died. I would like to say that this is just a myth. It will have no difference whether we are synthesizing through conventional routes or through microwaves. Absolutely, there is no difference.
Correct, absolutely right. So there is no difference between what kind of synthesis, whether you are doing any kind of physical or chemical or biological,
Exactly.
but only the condition is you have to take precautions. That is the most
That's right.
important for doing synthesis.
That's right.
As the particle size is smaller,
Yeah.
there may be chances of entering to our immune system or body
Yes.
system, right?
Yes. So
So that,
those, precautions one needs to take.
yes,
Otherwise, microwaves definitely will not change in any other way. They will not make it more toxic,
yeah.
for sure.
Otherwise, you cannot eat puff or cake.
Yeah. Exactly.
Okay, thank you very much, Dr. Amrish Dhave, for your wonderful presentation, completing for introduction to the end users. How can you take this commodity to the farming community? Ultimately, we are all working for the farming community. There is no doubt at all.
Exactly.
So, on behalf of the University of Future Sciences and the Center for Nanotechnology, I extend my sincere thanks to for your informative session. I can say, you touch all the areas. Even there is so many questions has been asked by the our scientists participants, and you have covered everything. And whatever there in the chat box, I will share with you, and we can make sure that all the things will be uh,
Certainly.
get answered for their queries.
Certainly.
Right. So thanks a lot for your nice presentation. And there is a small queries they are asking. So if it is possible, you can share. They are asking, is it possible to get these presentation slides? So generally, I
Yeah,
say
I can make a PDF document of this and send it across to you. Will that be fine? And then
yes,
you can probably distribute them to the users.
definitely, definitely, definitely. Okay.
That's very much possible. Yeah.
Yeah, yeah, yeah.
Sure.
Thank you once again. Thank you very much for a great day for your great presentation on the
Thank
first
you
day
so
of
much
our.
for having me here. It was a pleasure.
Yes, yes. Bye
Have a
bye.
nice day. Yeah.
Yeah, bye bye. Take care,
Bye
sir.
bye.
Take care. Bye,
Yeah.
bye.
Bye.
So this is for the yeah, announcement for the rest of the presentation of the day one. We are trying to get the second presenter, Dr. Vivek, from the homogenizer Biojet Mumbai. So you know very well because of this heavy rainfall, they are unable to connecting. Even they tried. Airtel, Vodafone, so many networks, but still, there is a problem with sharing their PPT. They're unable to connect till now also. So for that, I really, excuse for the non-availability of the Dr. Vivek, and he promised me that remaining days definitely he will join and do the presentation for application of homogenizer, that is actually a high pressure homogenizer, almost 60,000 psi they're working. Even they have the instruments more than 1.2 lakh psi also. So it's a wonderful information, but due to some problems, so they are unable to join for this particular session. So anyway, so thank you very much for your participation for the day one, which is successfully completed. We were supposed to complete by 4:30 for both the sessions, but somehow we have completed by 5 minutes early. But so as I already told you, there will be a feedback link will be shared with you through the mail what you have sent in your registration form, and also I'll just put in the telegram link also. Kindly fill it because the feedback link will be open for only 2 hours, so it will be from 5 to 7 p.m. So then later on it will be closed. And the for the tomorrow's session, so we have morning session. We have one speaker, that is Dr. Dattatreya M. Kadam. He is a principal scientist, ICR Circuit Mumbai. So he is going to deliver a lecture on application of nanotechnology in food processing and packaging. And the schedule is morning 11 to 12:30 p.m. And in the afternoon session, we have two experts. One is from Thermo Fisher. So he's Dr. Amit Joshi. He's going to explain the UV visible spectroscopy for its applications. And Dr. Sandeep is going to explain from the MAL1 particle size analysis and its applications. There are two wonderful sessions in the afternoon and one session in the morning session. So kindly join with us, and the tomorrow's link is going to be shared again in the Telegram group as well as in your uh, mail ID what you have sent in the registration form. And same thing also, if those who are viewing in the Facebook of my Facebook, that also I will share in the Facebook also for the tomorrow session. Every day there is a link is separate. The same link is not going to be used and it is not valid also. Due to the security reason, we are not using a same link. So the link will be changed every day. So kindly bear with us for any kind of inconvenience happened during the sessions. So because we are doing in the pandemic situation, this webinar is hosted across the country and collecting the across the experts from the different parts of the country as well as in the international scientists also. Once again, thank you very much for your presentation. Because in the morning we have a good numbers, but in the afternoon we have less numbers. I don't know. And already I mentioned very clearly. So it is recorded. 80% attendance will be considered for the issue of certificate. It is very clear. So if any less of attendance of 80%, we are not going to issue any kind of certificate for the participants. So this is for the information to all the participants. So kindly bear with the rules and regulations framed by the uh, committee. So thank you very much. Take care. Stay home. Be safe, and enjoy the day. See you tomorrow. Bye bye.